In the final essential task of Unit 2, we are going to add the final step involved in looking at the results of an experiment, and that is to conduct what is called descriptive statistics. You've likely heard of these at some point in your academic career, at least a few of them. Ones like mean, median, and mode, also other ones like range, though there are a few that you've likely not seen too frequently, such as standard deviation, and some of the normal distribution curves that we're going to be looking at in today's essential task, and then again in a later unit. I think this concept map could be held horizontal or vertical. It is the 7 total boxes that you see here, where we define descriptive statistics there at the top. There's a pretty big picture of a bar graph there. And then we identify what's called central tendencies, and then end with talking about variance. So I'll go back to the text of the essential task, give you a moment to pause the video, and copy down the yellow portion. We're going to start at the top with the definition of descriptive statistics. You can use descriptive statistics at the end of an experiment, as I was just alluding to, but you also use descriptive statistics quite commonly in other settings. For example, at the end of every year, sort of right after the AP exam results come in, I calculate a bunch of descriptive statistics. I do things like the mean, median, and mode relative to previous years. I do the standard deviation relative to previous school years. So I run a bunch of descriptive statistics at the end of a school year, which is, of course, not an experiment. So descriptive statistics are just any of the type of statistics that we talk about in today's essential task that aren't jumping to conclusions. We have inferential statistics from 2.5 for that. We're talking about things like the mean, the mode, the range. Often, not every time, but often you can see descriptive statistics summarized with a bar graph. As you can see here, this looks like a bar graph for some type of treatment method. Could be some type of pharmaceutical drug, trying to determine whether or not the placebo compares to the control group, or as the control group compares to the 2 experimental groups. It looks like there's a 10 milligram and 100 milligram experimental group. So that's an example of a bar graph that summarizes the results, in this case, of a pre- and post-treatment pharmaceutical drug study. In terms of descriptive statistics, there's 2 categories: standard deviation, or rather central tendency, and variance. We're going to start on the left with central tendency. There are 3 different types of central tendencies: mean, median, and mode. 3 terms that you've assuredly heard at some point in your academic career. I've provided the definitions here very briefly for you, in case for whatever reason you flip them or confuse them. But the mean is just another word for the average, so the class average. The median is the middle point, meaning let's say you have 9 scores. It would be the 5th one in, so the exact middle point between all of the scores in your distribution. Then, of course, the mode, the score that is the most frequent. The only thing that's worth noting that you likely haven't heard in previous classes is that, let's say you're doing an evaluation of your class results on a test as the teacher. The mean is generally very useful. That's why there's that green thumbs up. It's usually the best option. It usually summarizes how well your students did the best. However, if a student gets caught cheating and all of a sudden gets a 0, the class average is going to be dropped by a considerable degree. And now all of a sudden, what would have been an 85 class average drops to a 72 class average. And that 72 is really no longer typical of how your students did. It doesn't do a very good job of summarizing the class results. So under the circumstances of outliers, you then transition to looking at the median. The median is sort of the second best option, and it's absolutely the best option when there are these really ridiculous outliers. For example, if somebody really rich moved into our school and all of a sudden I asked what the family income level was in our class, and we have the child of a billionaire in the class, I don't know about you, but the idea of making $3-4 million isn't really typical or a good summary, at least of my financial well-being. So that would all of a sudden distort the results. The class mean for family income really wouldn't represent the class very well, because one outlier would be taking it off the charts. So under those circumstances, you ignore the mean and you transition to the median. One of the most common ways of visualizing the results of something like a test is to use a distribution curve. It's this nice sort of bell-shaped curve, or at least in this case, skewed bell-shaped curve. We call these distributions and distribution graphs. The 2 that you see at the bottom there are what we call skewed distributions. This is what happens when you try and graph the results of something like a test, but there's a major outlier. Somebody got a 0 on a test, somebody has exorbitant income, so it can be an outlier that pulls the mean really high, or an outlier that pulls the mean really low. And as a result, you sort of have this asymmetrical looking distribution curve. As a result, we call these skewed distributions, and we have 2 specific names for the graphs that you see below. I'm going to provide you kind of a silly mnemonic here, and it's going to seem pretty silly. I've had students find it effective though, so we'll explain it, go with it, and we'll see if it's effective for you. But I'm going to start with the one on the left. The one on the left is what we call a negative skew. Now, typically, if I were to ask students what they would guess each of these are called, they're usually the opposite of what your brain kind of wants. So this one on the left, although it kind of looks like the peak is heading in a positive direction, it's actually considered a negative skew because that tail, the end here all the way on the left, I like to call it the tail, is being pulled back down towards zero, because that's precisely what it would look like if a student got a 0 on a test and you were to draw that into a distribution curve. The results are being skewed in a negative direction. Thus, we call this a negative skew. This is going to sound sort of silly, but if you kind of visualize what your left shoe would look like, or what your left foot would look like with a shoe, it actually kind of looks like a negative distribution. And the word left has an E in it as that second letter. The word negative, unlike the word positive, has an E in it as its second letter. So if you can't memorize it using other means, or you're going to get confused because honestly, what you anticipate might not match the reality, I propose this mnemonic. You see that E in negative, you think of the E in left, you look at your foot, your left foot kind of looks like a negative skew, particularly depending on the type of shoes you're wearing. But sort of your big toe is up here at the peak, and then it sort of decreases downward. On the opposite end, we have a positive skew. That's what would happen if a really exorbitant person moved into Freetown Lakeville and the class income level jumped off the roof, saying that we have like a $3-4 million income level per family. That would be a positive skew. That's what happens when somebody pulls that number off the charts. In a similar fashion, when you look at the word positive, I see an I as that fourth letter. The word right has that second letter as an I. And in terms of at least the first few letters, the first 4 letters specifically, I is unique to positive. I know the TIVE at the end has an I in it, but that's shared between the two. In terms of just those unique 4 letters, I isolate that I isolate that E, and I use that as a mnemonic to differentiate these. Because it's common to see these graphs on an AP exam and be asked to identify which is which. And again, as I alluded to, if I go back and remove these feet, it's kind of the opposite of what your brain wants. I know the peak is more towards what would appear to be a higher number, but this is what it looks like when it's skewed as a result of a 0. Alternatively, I know the peak kind of looks like it's heading towards a 0, and you might want to call that a negative skew. It's actually a positive because the mean is being pulled forward, being pulled up way higher than it's really typical of the class or really typical of the distribution due to an outlier. Positive skew, right? We have the mean of a 70 here, representing family income levels, when that's not really typical of what the class looks like, because we have, Tom and Giselle pulling the numbers up way off the charts. As I alluded to earlier, when this mean pulls it up either too high or too low, we then look at the median. The median then does generally a pretty good job. The other concept is what we call bimodal distribution. Not every distribution graph for scores on a test has that perfectly symmetrical look to it. Sometimes you have what's called a bimodal or a multimodal distribution, where I've identified the mean here in the middle with this green. Let's say the mean on, for whatever reason this test was a 60. You notice there is a peak on either side. That basically means a bunch of people did really well on the test and a bunch of people did really poorly on a test. This is probably what a math result distribution might look like, where you either know it or you don't, meaning a bunch of people scored an 85, but a bunch of people also scored 35. And when you put those together, the mean might come out to approximately be 60. But all of a sudden, that mean is not even close to what the mode is. The modes are these really 2 high points here. So we call this a bimodal distribution. If you're a teacher and you get results like this, it basically means a bunch of kids got it, a bunch of kids didn't. And in theory, you need to find a way to pull those kids who scored below the mean up towards the mean, or hopefully even above the mean. That's precisely what it means when you have a result like this. Zooming back out to conclude our concept map, we briefly will talk about a concept called variance and the 3 boxes over here on the right. The term variance can sometimes be called variability. I've really only seen this once, but I've essentially seen a question where it asks, what is the variability of the study? And that was a fancy way of asking to either describe the range in the study or describe sort of a prediction of what the standard deviation would have looked like. In just a moment, we're going to define range and standard deviation. But when you hear the word vary, it basically means, are the scores similar? And there's 2 ways of calculating that. Are the scores sort of as a whole similar? Not what the average is, not what the median is, not what the mode is. Mode and similarity might come across as 2 things that are within the same realm. But when we talk about variability, it's kind of more big picture, like looking at all the results of this test or this study, all the results in your control group or your experimental group, whatever it is that we're using these statistics for. There's 2 calculations that we can use to answer the question. So if you ever see the question, like, what is the variability of your test scores or your control group or your experimental group? There's 2 ways to approach that. You either can tell the person the range, or you can tell them sort of an approximation of the standard deviation. We'll start with the easy one. We'll start with range, because it's likely a term that you've heard before. Range is just the difference between the highest and lowest scores in a distribution. So if the scores indicated there on the left are the scores that you got on some assessment, 15 is the highest, 3 is the lowest, the difference there is 12. 15 minus 3 is 12. So the range is 12. It kind of gives you a snapshot of how similar the scores are because you have a snapshot of how far apart they are. Alternatively, the one that you've likely not heard of, the one that's likely new to you, is what we call standard deviation. Standard deviation, by definition, is a single value, and it tells you, on average, how far every test or every score in the distribution is from the overall average. So, for example, if you take a test, the teacher looks at the results, and the teacher finds out that the standard deviation is 5. That tells the teacher, on average, any random test in that distribution, in that class, is about 5 points away from the class average. So if the class average was a 90, that tells the teacher that certainly there are kids that got in the 70s, certainly there are kids that got a 100, but on average, each test was 5 points away from that class average of a 90. What's unique about the standard deviation is, I'm going to start with the second bullet here and then go back up to the top one here about adding 10 points. But in theory, and this is how it plays out, if you look at these two distributions here, test 1 and test 2, notice how test 1, basically all the scores are similar. It's a very low range, 99 to 94, range of 5. All the scores are really close to each other. Then you look at test 2 and you notice 100 all the way to a 50. Notice how the ones on the left are really close together. Without even needing to know how to calculate standard deviation, it's kind of another one of those that you don't need to know the formula. You can just look at test 1 and say, whatever that standard deviation happens to be must be really low. All of those scores are really close to each other. So if that class average is 96, the standard deviation might be 1, might be 2. It's going to be really close. Alternatively, if you look at test 2, if that was a real test, a teacher would very easily look at those results and say, wow, my range is 50. My standard deviation must be significant. The test or the class average for test 2 might be 75. The standard deviation, though, might be 20 or 15 because of how spread out those scores are. The standard deviation is essentially one number that gives you a snapshot of how spread out the scores are in your distribution or within your class. In theory, as a teacher, you kind of want lower standard deviations with high class averages. That means basically everybody did pretty well, everybody scored well, and everybody's test was close to each other. The bigger the standard deviation as a teacher kind of tells you that there's a bigger range in how well students evaluated and understood that material. Now, this caveat here, if you really understand standard deviation, this will make sense. If I added 10 points to every single one of these scores, it wouldn't affect the standard deviation because this would turn into 109, 108, 108. All of these scores would still be really close to each other because I added 10 across the board. Alternatively, the same is true for test 2. If I added 10 to all of these, yeah, this would go to 110, this would go to 60, but it wouldn't change how much they vary from each other. They would still be incredibly spread out. Now, if I started adding 10 to specific scores, that would make this different. But if I added 10 across the board, it wouldn't affect how spread out these numbers are. It wouldn't affect the overall standard deviation. So there is a way to calculate it of which you do not need to know. You just kind of need to be able to look at test 1 and say, whatever it is, that's low. It must be like 1. You see this set in test 2, you say, wow, that must be a really high standard deviation. And if you really understand that concept, that it's a single number that tells you on average how far each test was from the average, that other point will make sense. That if you add the same amount to every single test in the distribution, it's not going to affect how spread out the tests are. But what is important is all of the central tendencies will change. If you add 10 points to everybody's test, the mean has to change, the mode has to change, and the median has to change.